HDMI dran, oder was?
Ich habe das an HDMI dran, ja. Aber der... Here we go. Gut. Dann, okay, then let's start with whatever we need to do. Okay, good. So, the last series, the last part of this series, and today we talk about lattice-based cryptographic constructions again. Last time we saw how we can construct lattice-based signatures. And the security of these things was based on the short integer solution problem. Today we look at lattice-based encryption schemes, and for this we'll use the LWE problem, learning with errors problem. So let's go right to the definition of this scheme. Okay, so here, we want to design a public key encryption scheme, which means, and I will only show how we can design a semantically secure or CPA secure public key encryption scheme. If you want to achieve CCA security, you have to use one of the known constructions of getting a CCA secure encryption scheme from a CCA secure encryption scheme from a CPA secure encryption scheme. To define the scheme, we need to define three things: the key generation, the encryption, and the decryption. Then we have to prove correctness and argue for the security. So for the key generation, we have the following parameters. N, M, and Q are natural numbers. Q is a prime number, and M should be at least 5 times N log Q for reasons that we see later. And S is a parameter depending also on M and should grow faster, asymptotically faster than square root of log M. This is our typical function, square root of log M, which means that we are, this was too much for it already, and it doesn't look good. The beamer is on. If I switch it off, it's not very good, I guess. Außen wieder einschalten. Ja. Still blinking? Anything happening? Yes. Sagen, die schwimmt in Geld, aber hier haben sie noch so einen museumsreifen Beamer dran, oder? Der blinkt hier auch nur auf und sagt gar nichts sonst. Seid ihr, ist vielleicht der F2 211 frei oder nicht frei? Also ist er. Ah. Das klang gerade wie so ein Dia-Projektor. Ja. Noch 14 Sekunden bis zur Selbstzerstörung. Okay, good. So we can continue. So this S, as I said, is a parameter growing faster than square root of log m, which means, if you remember it, that e to the minus s squared is a negligible function in M. Goes faster to 0 than any inverse polynomial. The square here takes care of the square root over there, and then we have the log m, and there we have omega. So it's all nice and it's easy. Okay, so furthermore, but the dZr is a discrete Gaussian distribution on Z with deviation or parameter r, which is of the form alpha times q, and I will determine later the alpha. Okay. We'll have other Gaussian distributions as well. But for those, I will give you the parameters immediately. Now, the key generation works as follows. We pick a matrix A from ZQn times n uniformly at random. And we pick an x from Z to the m with deviation parameter s. Okay? And then we form the vector u, which is a times x mod q, which is a vector in ZQ to the n. And then the public key is a comma u, and the secret key is x. Okay? And sometimes you will see that people call this, they form a bar, say, which is a concatenated u, or with another column u. Okay? And then if you multiply a bar by minus x comma 1, then you'll see that this beamer is no longer working, I guess. This is. Was machen wir da? Gehen wir in den Besprechungsraum? Lohnt sich das? Den Fernseher.
Du könntest auch dein iPad direkt auf den Screen sozusagen Also das wird für dich. Man kann den Spiel gleichzeitig encrypten.
Ich könnte das ja schnell in Zoom machen.
Oder so.
Okay. Das machen wir jetzt schnell. Okay. Und dann schreibe ich aber trotzdem was an. Vielleicht.
Ja, ich habe.
Okay, anhalten. So, dann muss ich einmal. Okay, ich mache das bei mir in meinem Meetingraum. Kannst du kurz die E-Mail, den Link schicken? Dann kann ich hier das schon.
Meetingraum also. Ja, du meinst für.
Weniger immer, genau. Starten.
Ja, Meetingraum von.
Inhalte teilen. Jetzt kann ich hier wieder nur den Bildschirm oder sowas teilen. Which is not necessarily. Ja, wird schon klappen. So. Ja, gut. Soll ich hier das Mikro lasse ich mal aus, ne?
Ja.
So.
Ja.
Bist du schon drin, Laurenz? Siehst du die Folien? Oh, du bist auch drin, okay.
Also konnte ich noch einmal kurz.
Ja, ich wollte nur.
Nicht.
Dann stelle ich mal hier. Drücke ich mal hier auf Aus. Ja. Kannst du das dann beides gleichzeitig machen? Okay, das ist ja. Hätte man das die ganze Zeit so machen können. Ne?
Schon.
Okay, good. Continue?
Continue.
Okay, good. So we have this public key A comma U, and the secret key is this X. And we know that if we have built this A bar, which is A concatenated U, and then we multiply this A bar with minus X comma 1, then this gives us the 0 vector. Okay? Which means that we kind of know, recall that X, we pick this with this parameter S, and we know that X is short with high probability. It's roughly of the length square root n times s. This was one of the bounds on discrete Gaussian distributions. So this is the secret. And let me write down here on this side here Al-Jamal. And then we'll see what we get from here. So keygen for Al-Jamal. We have this ZP, and we have a G as a generator, and we have, say, X, which is our secret key, which is in ZP star, and then we have the public key, which is G to the, which we call H, say, which is G to the X mod P, okay? And so the public key, the secret key is X here, and we hide it in this H. So here we hide the secret key basically in this vector U. Okay? And X is a short vector for that solution. Okay? So again, we use the same technique that we basically use in all of these public key encryption schemes. We hide the secret key in this public key, okay, in a certain way. So now how do we encrypt? And the scheme works in the form I presented, works only for encrypting single bits. But then again, if we have a CPA or semantically secure encryption scheme, then we can just encrypt individual bits individually, and we still get something that's CPA secure. Or security against, if we have indistinguishable encryptions, we have also multiple indistinguishable encryptions for any CPA secure encryption scheme. Okay, so now what we do to encrypt a bit, we first pick an element S uniformly at random from ZQN. And then we pick another vector E according with m+1 coordinates. Each coordinate is picked according to the distribution dz, r. Okay? So this discrete Gaussian distribution, we pick that m+1 times. And we partition E into the first m coordinates, which form the vector E bar, and the last coordinates, which I just call EM+1. And then our ciphertext consists of two components. The first one is a vector. It consists of A transpose times S plus E bar mod Q. So A transpose is a vector that has now n columns, so we can multiply it by S. And what we get is a vector of length m. So we can add E bar. This is really, these are, as we review them later, these are m samples according to the LWE distribution. Okay. This is our first component of the ciphertext. The second component is a single number, mod Q. Here we compute U transpose times S plus EM, and then we add mu times Q half rounded mod Q. So if mu is 0, we don't add anything. If it's 1, we add Q half rounded. Okay? And the ciphertext is C1, C2. Okay? So let me see. So encrypt in Al-Jamal. What we do is we pick this R uniformly at random from ZP minus 1. We have, then we form this C1, which is h to the r mod p, and we form C2, which is, sorry, we form g to the r mod p, and C2 is h to the r mod times m mod p, where m is a message. Okay? Okay. So again, what we do here is we have this random element, and this first part here tells us, okay, look, this is the random element, but I don't tell you exactly what it is. And then I use the second, this public key to encrypt. Okay. Okay. And what we do here in this part here is similar. The S plays the role of this R, the vector S. Okay. I'll use that S in C2 with U to actually encrypt the message. The first part is completely independent, is independent from S. But as we will see, the first part will help us to decrypt. Okay, and how will it help us to decrypt? Well, if you can also view this equation that I have here, so as A bar transpose times S, right? This is, and then I add here this whole vector E. This here gives, this is also C1, C2 mod Q. Oh, not quite. Actually, plus E plus, and here I now include a vector has all zeros, except in the last coordinate where it has this mu times Q half rounded mod Q. Okay? This is all in one equation. But as we'll see, yeah, this is an alternative way of describing it. But again, it's good to compare that to Al-Jamal. We pick something random, but we use the first component to tell somebody who knows the secret key actually what this guy is, or actually have this guy then is able to do something with the second component, which you are not able to do with the first component. Okay? Now and that leads us to the decryption algorithm, and maybe I write down here what we do. So what we do to decrypt with the public key, we simply compute C1 to the minus X, right? And multiply that with C2. And if you look at it, this gives us exactly M mod P. So we are not really recovering the R, but what we are doing with the secret key, we can sort of cancel it out. The part that depends on R in here, we can cancel it out without really knowing what this R is. Okay? And we'll do this similar thing over there. So what you can also look at is, you can view this here, this operation here, and this operation here as the equivalent to the exponentiation. Right? This evaluation of this inner product and then of the LVE samples. It's like the exponentiation. Okay, so now how do we decrypt in this case? Well, we use actually this thing here, or the fact that A times X is U. Okay? So here it is. So decrypting a ciphertext, we get this C, which is C1, C2, and then we compute this V, which is C2 minus X times C1. Now you see the striking similarity to what you have here. Right? Write everything as if it was an additive group instead of a multiplicative group. The formula is exactly the same. Right? So, and you do that mod Q, but then you are not quite done. Here you are done, but here you are not done. What we do then is we do a check, namely if v is closer, so remember v now is a number, if v is closer to 0 than to q half rounded, then we output 0, otherwise we output 1. Good. Okay. So what is this term here? This v. If you look at it, our C2, remember our C2 is, so this is U transpose times S plus EM plus 1 plus mu times Q half rounded. No, this is C2 minus, now we have to, oh, sorry, this is a transpose. Just formally, it's just a transpose. And here we have what is C1. Then we have here the X transpose times C1, but C1 is A transpose times S. And then we have another component, namely X transpose times E bar. If you look at our C1, you see that this is actually what we get. Yeah? Mod Q. Now, the interesting thing here is that obviously here, U transpose is, U was, let me write this down, as U was A times X. So U transpose is X transpose times A transpose. Yeah. And then you see that this here and this here cancels. Yeah. And why is it important that these two things cancel each other? For these two things, we have no control over their length or their size. Right? Because, well, S is from ZQN, and A is also just a number, a matrix. Okay? So we have no control over their length, but these two things cancel. Okay? And now what's left here is exactly this EM plus 1 minus X transpose, or let me write it differently. I'll write this in this form. This is minus X transpose times E bar plus EM plus 1 plus mu times Q half rounded down. And this here I can also write as minus X comma 1 transpose times my original vector E plus this mu times Q half rounded. Okay? Not Q everything. Okay. Okay. So I do get this mu roughly, but I get this kind of this error term, this dirt. And if I did not have this here, yeah, this error term or this dirt, then obviously my decision in the last line is correct. Right? So what I now have to argue is that this term here with high probability doesn't screw up my decision. And when will it screw up my decision? Well, let me maybe do this here. So we have here, say, well, let's do it. We have here 0. We have here minus Q half. Here we have Q half. Okay. So so this is the encryption of 0. This here is the encryption of mu is 1. Now, you can see that I can add something to it, but it shouldn't get too close to this here. And I can subtract something from here or add this, and it should get too close to this here. So I need to stay sort of in a little range around this here and a little range around this here. This is actually, it's like a circle again, right? And in the extreme case, you could do it up to q divided by 4, right? Below it, because this is really, then if I add at most q 4, then it's still closer to 0 than to q half, or q. And also in the other case, if the bit is 1. Okay, so, but we'll be a little bit more careful. And I say that the correctness, this is correct if we have that the length or the size of this term here, of this guy here, can be bounded by q divided by 5 with probability almost 1. So I'm a little bit more careful than q divided by 4. So that, if that is 2, then we are done. And this is over the choices that we make in this, in the encryption. And in the encryption, we pick x to be from dz to the ms here, and e according to this distribution here. Right? Okay. Note that we add to x this coordinate of length 1, but that's a short one. Okay. And so what we can do is, and this is where we get all these parameters from, we have this discrete Gaussian distribution. This is our deviation. And then what you can show is, don't want to go into the details. In papers, you will probably often see the term that's a sub-Gaussian, which means that it behaves like a Gaussian distribution almost. But what it is, it's almost a Gaussian distribution with mean 0 and deviation at most s times r times square root of m plus 1. So what we do is here, the terms in this x are all bounded roughly by, so the length of s would be sort of with high probability s times square root of m, Gaussian distribution. The plus 1 comes from the fact that I add this 1 in there. Okay? But all these things in the individual coordinates get multiplied by this e. Okay? But this e, yeah, you can argue that it's bounded by r, sort of, or the deviation is r, but you need to be more careful than that. Okay? It's a sum of distributions. Basically, it's what you get is a sum of Gaussian distributions where each has parameter s times r. The deviation from x and the deviation from the e's in each coordinate multiply. You have dimension m plus 1, and that's why you get this here. So the deviations multiply in each coordinate. You have m plus 1 coordinates, and that's what you get. And the mean, because each coordinate of x has mean 0, blah, blah, blah. And then you also have the sum of these things has mean 0. And then we know from our previous courses that a Gaussian random variable with deviation r bar satisfies this condition here. Okay? Now we plug in for t. This is our Gaussian distribution. Our t is this term here. Right? Okay? And recall that r is alpha times q, so this gets in here, this is s, and then I just look at this term here. Right? So this is just this, maybe I'll just do this here. Then so what we want basically is that this term here is negligible. So, and this term here becomes this guy here if we plug in the parameters, and we want this to be negligible, so it should be omega of log n, because the square is gone. I already included that into the t square r bar square. Okay, and then you just play around a little bit, and then you get that alpha is roughly of this size. Actually, there's a little omega involved in here, so this log n should be omega of log n or something like that, because we need this omega somewhere. And there are constants involved that I ignored. Right? But if you look at this here, this and this cancels. That's a good thing. The q goes away. Right? The m is the one that we get down here, but it's a square for alpha, so that's what we get there. Okay. Okay. Yeah. Okay, so we need to choose this alpha in this range, roughly, to get correctness with high probability. Yeah. So the important thing is really always remember Al-Jamal. Forget RSA. RSA is an accident. Is it really an historical accident? Al-Jamal is because if you want to use RSA in a meaningful, secure way, you have to do that. You can't use it in the textbook version, and then you have to do something like this here anyway. Al-Jamal is the one thing that's the prototype of a public key encryption scheme. You have two components in the encryption. One that includes a random element, and the second one also includes this random element, but the first component helps you to get rid of the second component of this part depending on the random element. Okay. And here we do the same thing with this u and 8x, which is a times x, but then we have these error terms. And remember that we need these error terms because otherwise we are talking about equations that are exact, linear equations that are exact. And exact linear equations are easy to solve using Gaussian elimination. Yeah? That's why this makes this look not quite so nice. We get a similar equation here that's almost the same as there, but the sort of the decryption rule, the decision rule at the end must take into account that we have these errors in there, these error terms. And that's why it's more complicated. Okay. Okay, but this doesn't say anything about security, right? So far. Okay, good. So how do we prove security? And what I will argue is that, so we look at a CPA adversary against a lattice-based encryption, right? And I will do the technique called so-called game hop or hybrid distributions. And by that, we'll turn what the adversary sees, which depends on the message, into something that's independent of the message. But the distributions are indistinguishable for an adversary. And once we have done that, we are done with the proof. Because then he sees something that's independent of the message, he can win the game only with probability 1/2. Yeah? Okay. So in the game CPA, and recall there's no decryption queries in there, what the adversary really sees is the public key and the ciphertext. So this is the stuff that he sees. Oops. Here is the stuff that he sees. Okay. He sees A, which is a public parameter, or actually part of the public key. He sees the U, and then he sees obviously the two components from the ciphertext. Okay. How are these distributed? This is the distribution D0, which is the distribution on ZQ n times M, that's the A component, ZQ to the N, that's the U component, ZQ to the M, which is the C1 component, and ZQ, which is the C2 component. And I wrote down here in these lines here how these things are generated. Okay. Now, the first hybrid, we are not just replacing the C component by something that's independent of the message, but we also replace X by something. We kind of decouple. We want to get rid of the secret involved as well. Okay? And this is the first thing where we look at the distribution D1, which is on Z on the same 4 tuple, but here we choose A as before, but U is picked uniformly at random from ZQ to the N. There's no X involved anymore. Okay? The rest, the components C1, C2 are generated as before. They are generated in the encryption. The encryption doesn't use the secret key. So we can still use the same way to define C1, C2. Okay? Okay? So then we'll check that the two distributions are indistinguishable for a polynomial time adversary. In fact, they are statistically indistinguishable. And that is by, recall from lemma 4.10, I'll show you that with probably 1 minus 2 to the q minus 1, the two distributions are statistically indistinguishable. So there's a small probability that the distributions are not indistinguishable, but the probability is 2 times q to the minus n, which is negligible. And given that we are in the good case, this is only over the choice of A. They are bad A's, namely those that don't have full rank. But other than that, that's working out fine. And maybe I'll just show you where this is. Here it is. The lemma 4.10 said that if I pick my E from this distribution that I also use in my construction, namely here, then A times E, this U, is statistically close to uniform over ZQN, where S is S in our construction. That's where the S comes from. And that happens for all but a 2 times q to the minus n fraction of A's. So that works out nicely. Okay, so we can go back. So this is the first hybrid. Now we need to get rid of the second hybrid. We need to replace the second component, the C component, C1, C2, by something that's independent of the message. And so here again is the first hybrid. And now I replace the second component simply by picking C1 to be a random vector, ZQ to the M, and C2 to be ZQ. And that's it. Huh? And you see now, if an adversary gets this part here, and he has to guess what mu is, it's independent of mu, probability 1/2. Okay? And the deviation, the distance to 1/2 comes from the statistical closeness or indistinguishability or computational indistinguishability. Okay? So far I did not use the LWE construction. So obviously, and now I'm doing it. That's exactly what I'm doing because this here is an LWE. These are LWE samples. This part here is an LWE sample. This part here not. But don't worry, if those are LWE samples, they are indistinguishable or computational or statistically indistinguishable from random stuff. Right? Now if I add to a uniform thing, mod Q, a fixed element, that's still uniform. So I don't need to worry about this part here. Right? If I can argue that this here is indistinguishable from uniform and this is indistinguishable from uniform, then I'm done. Okay? But now also recall that because I already replaced U, which was originally A times X, by an independent stuff, independent from A. What I get here really, this part here together with this part here, are m+1 samples according to the LW distribution. Okay? This would not be true if I kept X to be in this form A times X, because then U would depend on A already and these samples would not be independent from each other, which is important. Huh? But in this form, they are independent, and then I can, then I can just say by theorem 1.19, and assuming that decisional LW n, Q, with the distribution dz, r is hard, then the two distributions are computationally indistinguishable. And for that, we needed this alpha q to be at least 2 times square root of n. And maybe I show you this other, where is it? LWE should be somewhere here. SIS. Here it is. Right, that was the theorem. And here, again, here we use that we assume that gap SVP gamma or SIVP gamma are cannot be solved even with a quantum computer. If that assumption is true, and we have all these parameters set as they are, then we know that this is computationally indistinguishable. Okay? But again, this only worked because I was able to replace U, which was A times X, by something that's independent from A. Otherwise, I cannot apply this theorem. And that's it already. Yeah, so then we get really that we have this stuff here. So combining everything, assuming that this decision LWE is hard, and we know that it's hard, given the theorem, if SIVP gamma and some are hard, then the lattice-based encryption scheme is semantically secure. And that's it. And then we are done. Okay. Okay, questions so far? Otherwise, I will do one more remark. So I want to make the analogy between Al-Jamal and lattice-based encryption even stronger. Why do I want to make it stronger? Recall that in Al-Jamal, in the lattice-based encryption scheme, I set A times X to be U, and PK was A, U, and SK is X. And then we had the encryption was a C1, which was A transpose times S plus E bar mod Q, and we had the C2, which was U transpose times S plus E M plus 1 mod Q. Okay? If you look at Al-Jamal, basically, to hide the secret key in the public key and to hide this random part in these components here, I use always the same operation, namely exponentiation. Right? Whereas here, it looks as if I use here something different than I use something different here than I do here. Right? The question is, can we do something similar to what I did? Can I replace this by something where it uses the same operation as here? And in fact, that is one variant of this encryption scheme where You don't construct U in this form. Instead, you do it something like A times S transpose plus some error as well. And then you sometimes even use a different distribution. Okay. Typically for some other S. Don't use the same. That won't work. Yeah. And then it's all the same. Well, it even closer resembles Al-Jamal because I always use the same thing. Right? Hiding stuff is always using LWE. And this is in particular important if you go to ring WE, where people do that most of the time, actually. Oh, look, you can do both things, but okay. And in fact, one can show in that case that you can even pick this S then to be not of full length, but you can pick a short vector to do that. And that's very important. It helps because then you have a short secret key. Short secret keys is always good because at some point, somewhere you have to store the secret keys. Short means less storage that needs to be protected. That's it. Okay, good. So, and that's it. To this thing here, just one more remark is that this is not the original scheme by Oded Regev. This is the so-called dual Regev scheme with little modifications. I picked the X differently than from what you sometimes see, where it's a 0-1 vector, uniformly random, and then you use the leftover hash lemma. But I already presented you that this nice Gaussian distribution lemma, which leads to uniform vectors, works as well, basically. So this is dual Regev, and it has many applications. And anyway, this stuff here, all the primal version you can use to construct in combination with other things to get many other constructions, like IBE, HIBE, ABE, homomorphic encryption, and similar things. Okay, and that's it, really what I wanted to say. Questions? Complaints, remarks? If that is not the case, then we are done with the lectures. In particular, I'm done with the lectures. Okay, good, thank you.